This might just be the most fun place I've ever given a talk. And Dr. Evans, that was amazing. I feel totally inspired and kind of lame going traditional here, so sorry. But they gave me the nickname Dr. Dynamo, which I love because my research team back at Arizona State University is called Team Dynamos because we all work on something related to magnetic fields. So Mr. B is our friend. Okay, so today I'm going to talk about Proxima B. Who's heard of Proxima B before? Okay, good. That's about half of you. Great. Proxima B is the name of our nearest exoplanet. It orbits a star called Proxima Centauri, and it will forever be our nearest exoplanet because Proxima Centauri is our nearest stellar neighbor. Okay? So we better get comfortable, because if we're ever going to have interstellar travel, this is the first place we're going. Okay? I'm going to talk a bit about that at the end. So, looking for exoplanets, right, and thinking about habitable worlds other than the Earth has been a long-standing tradition amongst the philosophers. Giordano Bruno wrote hundreds of years ago, "Innumerable suns exist, innumerable Earths revolve about these suns, and living beings inhabit these worlds." Right? He was eventually burned at the stake for this and other kind of things. It is true. My job security is a little bit safer than his. So thanks to him, actually my very first computer I named Bruno after him because I quite appreciated that. Now if you fast forward 400 years from Bruno, we now have 4,000 confirmed exoplanets. Did you guys know that? 4,000 with 8 planets on Earth. Wow, thank you. I'd like a here I'm showing you a histogram it's a cumulative histogram, and it's got year on the bottom, number of planets detected on the top, and it's color-coded by 2 main colors. Red, which is the radial velocity method. I'm going to explain these 2 methods to you because they're the most popular. And green is the transit method. The green one is mostly thanks to the Kepler space mission that discovered most of these exoplanets. And we are forever grateful to the Kepler space mission because it is thanks to Kepler that we now know that exoplanets are everywhere. Okay, and that in fact, another fun fact for you, there are probably more planets than there are stars in our galaxy. Wow. Wow! Who is that? Can this guy get a spark sticker? Okay. I love this. All right. And so some of these planets, not all, but some of them do orbit in what we call the habitable zone. And the habitable zone is this green ring around a star where liquid water, if all else was equal, and there was liquid water on the surface, and there was water on the surface, it could be liquid. So for instance, in our solar system, there's the Sun, Mercury, Venus, Earth spins in this green zone right here, and out here is Mars. Now, if you spin it, you see the Earth is happily in this green zone, but if you have a hotter star, the green zone has to move outwards. And if you have a cooler star, the green zone moves inwards. Why? Because if you are cold and you want liquid water, you got to get closer to the fire. If it's too hot, you got to get further from the fire, and that's why the habitable zone moves inwards for cold stars and outwards for hot stars relative to our sun. So now that I've told you that there have been 4,000 now confirmed exoplanets, I'm going to try and summarize these discoveries in a highly biased view of what I think are the 4 most important things we've learned. One is, as I said, exoplanets are everywhere. They're extremely diverse. They're in fact more diverse than the 8 planets in our solar system, and Pluto and all the rest, right? And you think that all the planets in our solar system are really different from each other, right? We're so totally different from Mars and very different from Venus and very different from Jupiter, right? There's a lot of diversity just in our one solar system, but the exoplanets span a much wider range of diversity in mass, in temperature, in density, in composition, and so on, in every which way. Of these, there are about 10 confirmed habitable zone planets. There are about 10 small planets, about the size of Earth, maybe a bit bigger, that orbit in that green zone called the habitable zone. And most of those are around low-mass stars. And if you look at some of the statistics, thanks to the Kepler space mission, about 25% of planets around low-mass stars, the lower-mass stars are cooler than the sun, lie in the habitable zone. And if you work out that there's 200 billion stars in our galaxy, 75% of them are cooler than the sun, that's roughly 40 billion small Earth-sized planets in habitable zones in our one Milky Way galaxy. Wow. Okay? Just everyone wants a sticker. Okay, I get it. Okay, so 40 billion in our one galaxy. Do you know how many galaxies there are? Another 100 billion, right, with a B. So this is amazing. I mean, I'm totally excited that we live in this time that we knew this. And we didn't know this 5 years ago, okay? This is new stuff. So I'm going to give you a little tutorial on these low-mass cooler stars, because if you want to know about the distribution of habitable environments in our galaxy, you're going to have to learn to love cooler stars than our sun. Okay? This is our sun. Looks familiar. Cooler stars are about half the size or smaller, and they're a bit redder because they're cooler. And if you plot them up this way, where you have, where you have mass going in this direction, which is the normal way. The astronomers will be confused by this plot because we usually plot mass in this direction. But that's okay. Let them be confused today. It's your night, right? Luminosity here relative to the sun. So the brightness is going up in this direction on a logarithmic scale. Here's the sun. It's a G star in yellow, right? And these here are all M stars, are all the cooler stars that are much fainter than the sun, much cooler than the sun, about half the temperature of the sun or less, and much smaller than the sun. And Proxima Centauri, our nearest neighbor, lies around here, and it's about 0.2% of the sun's luminosity. So what does that mean? Is the planet closer to its star or further than its star than the Earth is? Closer. Wow. Oh, you guys are funny. Okay. I knew I came to Austin for a reason. Yeah, this is it. Okay. I don't care. I take it where I can. So this here shows you the number distribution of stars in our galaxy. They're not like organized this way, right? They're randomly distributed on the sky, but it's just showing you that if you take the nearest stars within 30 light years, there's about, what is happening here? Hold on. Sorry, I'm learning this new thing here. So you have about 20 of these red dwarfs, these M dwarfs, to every one solar type star. Okay? So our sun is not your average Joe star. Right? Everyone says the sun is an average star. It's not. It's way rarer than these M stars. These M stars make up 75% of the whole galaxy stellar population. Now, let's talk about finding other worlds. I mentioned two of the most popular techniques, and we're going to talk about them. One is the transit method. Pretty simple, right? You just have a planet, goes in front of the star, and the total starlight drops, right, by some ratio of the size of the two disks squared. Okay? Pretty straightforward. However, in order for this to happen, you need to have a perfect alignment. You need to have the planet cut right across, just like you would have an eclipse. And when Venus eclipsed the sun, right? Remember that like a few years ago? With the total solar eclipse, right? Of 2017, that was essentially the moon just cutting. It's just much bigger, relatively speaking. But this is exactly what's happening. So geometrically, it's pretty straightforward. But you need this orientation. What that means is that there could be a planet orbiting in this direction, but you don't see it because it doesn't cut right across through the transit method. And there's lots of them. So in fact, it's only about 2% of planets cut right across that we can see this. So we're missing roughly 98% of the other stars. So we need this other method called the radial velocity method. And that is thanks to Lord Gravity, or God Gravity, wherever she is. And it's thanks to gravity that we can then see the gravitational tug of a planet around its central star. Okay, so you know the two two bodies are moving around a common center of mass. And so if you have a planet and it's tugging on its star, our planets do tug on our sun. So if there is a intelligent life forms with telescopes on other planets, maybe on Proxima b, looking at us with this method, they would detect Jupiter for sure with our current technologies, and maybe some of the inner planets as well. And almost get the Earth, almost. We're almost there, guys. And essentially, you either look at a spectrum where you look at the light from the star as it moves back and forth, back and forth. And what's kind of amazing about this is that the current record is roughly a few tens of centimeters per second. I don't know what that is in inches because I'm Canadian, but I don't know, a few. Okay. A foot, okay? But that's really slow. We're looking at stars. This is the starlight that's being tugged on by a planet because the star is moving back and forth at inches per second. Like, what in your life walks at inches per second? Your home tortoise? Like, what? It's really, really slow. And we're looking at stars, people, right? Moving at this really slow pace. That is the precision with which we are hunting for planets, which is remarkable and what was needed to discover Proxima b. So Prox b was, as we say colloquially, was found through this pale red dot program discovered by a good friend and collaborator of mine, Guillaume Anglada Escude, and his collaborators, where they are looking, using this radial velocity method, they are looking for planets around these red dwarfs, these M dwarfs. Why? Because their planets, the little Earths, are easier to find because they're closer in. Remember, they're closer in to stay warm by the fire. And this is a movie that he sent me, where you can see that they have many nights down. This was done in La Silla in Chile, in the dry Atacama Desert. And with these, with those measurements, those very, very precise measurements, they saw a Doppler wobble of only 1.4 meters per second. I'm not sure I could do this. Yeah, I could do one. I don't want to go too far, but it's pretty darn slow to find this 1.3 Earth mass planet at only 5% of an astronomical unit. So only 5% between the distance of the Earth and the Sun. Really, really close. And the orbital period, so the year of this planet, is 11 days. Ours is 365 days. There, it's 11 days. Okay? So of course, the natural question is Proxima b habitable? It is in the habitable zone. I already told you that, but that's only the first ingredient you need to habitability. Habitability depends on many things. It depends on the star's properties, right? If the star flares a lot, if Lord B causes a lot of trouble, then that might be problematic, but also on the planet's properties. Did liquid water ever arrive there, form there? What's its volcanic composition? All sorts of things. And so if you turn these into these kind of word clouds, you can start seeing just a few, and I wouldn't say this is even everything, of the things that habitability really depend on. Mass, luminosity, abundances. What's it made of? How fast does it spin? How old is it? What's its magnetic field like, or its wind? And for the planet's case, the pressure, the structure, and so on, dynamics, and so on. Right, there's another thing to consider when I did mention age, and that is that the habitable zone actually shifts with time, especially for, and shifts rather slowly for a low mass star. You can see the orbital distance is here, and Proxima Cent's current orbital distance is here, very, very close in. Remember, I said 0.05 AU. But the habitable zone changes because the star is evolving. So we have to consider all these things. So when you hear about Earth 2.0 discovered, you should wonder, is it really Earth 2.0? And start looking and dig a little deeper into the New York Times article that says this and that will claim this, and look to see, well, what's the star doing? What's the magnetic field doing? What's the wind doing? Right? Because we know that these M stars are actually much more active than our sun. They flare much more frequently, have super flares at regular time scales. And this next image that I'm going to show you is right off our sun. This is an actual movie of our sun, right? And this happens on our sun, not nearly as often as on M dwarfs, but we're also at a nice, safe 1 astronomical unit distance, right? Proxima b is right close to its star. So we still have to consider what it looks like. And this is another way that the magnetic field might actually help Prox b remain habitable, is if its atmosphere is protected from the nearby stellar wind. But we don't know if it has a magnetic field. So to answer the question, is Proxima b habitable? I would say it's complicated. And the last thing I wanted to say was talking about, can we reach Proxima b, right? So I said to you that if we were ever going to do any interstellar travel, this would be the first place to go. And for those of you who think we've already accomplished interstellar travel, we have not. Some people ask me that, children, especially if I'm in a school, and I say that I study exoplanets. Sometimes kids ask me, well, which ones have you been to? No joke. And I said, once I said, well, I haven't been to any of them. They're very far away. And this girl said, well, where have you been? And I was like, no joke. This happens. So I just wanted to clarify for you guys that we have not succeeded in interstellar travel just yet. The Voyager people are going to be sending me nasty emails. Wow. Okay. So currently the best that I can't really say a prediction, but I think the biggest effort right now is to send little tiny cameras about the size of your fingernail, right, accelerated by lasers on Earth that will be shot out to Proxima b. And so that, I think, is really in our lifetime. So I think that technology, which is being developed in California, at UCSB, and in other places, is probably about 15 years away, maybe. I have no idea the rate of technology, how it will increase. But within our lifetimes, I think we will be sending little tiny cameras to Proxima b. And it'll take, because they have to accelerate them to a significant fraction of the speed of light. So let's say the technology is ready to go in about 15 years, and if they accelerate it to the speed of light, say 20% of the speed of light, and Proxima b is 4 light years away, it should take about 20 years to get there, if I did the math right. And, but only 4 years to beam back an image, because the image will come via the speed of light. So in our lifetimes, we really could have a picture of what's happening on Proxima b. So I find this very exciting. And maybe there's oceans and continents, and this will be the way we know. So I want to leave you with one last image, and that is starting with what I originally started with, which was we now know that statistically all stars in our galaxy have planets. So next time you look up at the night sky, I know it's cloudy tonight, but the next time, don't just look at the stars, just imagine them all stellar systems. Thank you.
Thank you, Dr. Dynamo. We have some time for some questions. Yes, we're back up there.
Is it possible to know anything about the atmospheres of those exoplanets? Absolutely. Atmospheres have been detected now since 2002. And so through the transit method, there's multiple ways to do it. But since I showed you the transit method, I'll explain that, where if you have a planet that has an atmosphere passing in front of the star, the atmosphere is essentially backlit by the star. So you can see the absorption features of the planet's atmosphere, the light that it blocks, and you can find sodium, water, carbon dioxide. Trying to remember which other ones have been detected, but there are a bunch of molecules that have already been detected, and that is the way we want. That is what I think is going to be the soonest way we're going to find biosignatures. So gases developed, or that are gases in the atmosphere that are produced by surface life, is going to be done via that same technique.
Yes, the lady right here in the middle.
Who's in charge if we do find life on another planet? Well, it ain't me. That's for sure. There are actually councils. There are committees. I'm sure, and I don't know, but I'm sure. I'm 99% sure the government has a committee on this, on what we do. How do we disseminate this information? Maybe the UN. But it does exist. And I know people who have been part of these kinds of committees where they decide both if the evidence is real enough, if it's really confirmed by, the scientific method and multiple teams and so on, and then there'll be press releases, and then, it'll be really exciting, and hopefully our lives will be changed forever, or you'll just go back to doing the same thing you've been doing every day. I don't know.
So we have a Twitter question from @ImaginaryUnreal. Are there any or what upcoming telescopes that will help improve exoplanet detection?
For exoplanet detection, yes, we currently have a relatively new one called TESS, NASA's TESS mission. It's the Transiting Exoplanet Survey Satellite, and it launched back in April, and its sole purpose is to detect more exoplanets around bright nearby stars so that we can use the transit method to probe their atmospheres and do other planetary characterization.
By the stairs back there?
Great question. How do you actually confirm habitable planets if you don't have biosignatures or some other specimen? Is that what you said? Yeah. Well, we don't confirm them as such. So we can confirm that they're habitable zone planets, meaning that they're in that green zone, but we have not yet confirmed any habitable planets yet. Clear biosignatures have not yet been detected, but I think that probably within the next 5 years or so, we will at least have some indications. Whether they're ambiguous or not, I cannot say yet, but we'll have something.
Is that a question up in the balcony? Yeah, you. And Dr. Dynamo is going to be here during intermission, so if anyone that still needs a question answered, go ahead and answer. But last question up there.
Oh, interesting. Given that the period is 11 days around its star, what would gravity feel like at that? Gravity, if it's an Earth mass planet, gravity will feel like Earth. That's right, right? I think that's right.
It's all about the reference frames, right? Yeah.
I think you'll see, your year will be shorter. And so if you're tilted, your seasons will be shorter. And you'll have many more birthdays. But I don't think gravity will be different.
More cake. Yeah, more cake. More cake, right?
More cake.
Yeah. Okay, well, let's thank Dr. Dynamo. She's going to be here through intermission.